Welcome to Beyond the Qubit. I'm your host, Frank Dekker. My guest of the day is Yuval Boger, the Chief Commercial Officer of QuEra. QuEra is an interesting party to talk to because QuEra makes a quantum computer based on natural atoms, and they have very exciting partnerships with MIT and Harvard. So thank you for being here, Yuval. I'm excited.
Maybe indirectly bring up the issue of errors, of quantum errors. And quantum errors is really sort of one of the biggest frontiers in quantum science and quantum computing today. The challenge is that qubits are fragile. Whether they're individual atoms or photons or something else, qubits are potentially susceptible to many different things. It could be cosmic rays, it could be vibration, it could be temperature changes, it could be strong electromagnetic fields. Whatever the reason is, qubits are fragile. And then the control systems that you use are not perfect either. I mean, when you turn on a laser, it doesn't just go from off to on instantaneously. There is some curve of how it works. And as a result of that, when you make calculations, when you make operations using qubits, sometimes the operations go wrong. So simplistically, again, just taking sort of a classical example, let's assume that I want to do 2 plus 2, and 99 out of 100 times, 2 plus 2 will come out to be 4, and 1 out of 100 times, 2 plus 2 will come out to be something else. 5 or 3 or 0. Now that's 1 in 100. Even if it's 1 in 1,000, even if it's 1 in 10,000 times, these errors accumulate, right? Because to solve complex problems, you need long calculations with millions and millions of steps. So even if you had an error once in 10,000 operations, you're almost guaranteed when you do millions of operations that you'll get junk. This is where error correction comes in. Error correction allows us to detect these errors and correct them. And that's a super complex process. It basically involves, think about it as spreading the information from a qubit into a group of neighboring qubits. And instead of treating them as individual physical qubits, we call them logical qubits, a group of physical qubits. And then once in a while, you measure some of the physical qubits in that logical qubit group. You very quickly try to deduce if something happens. Think about it almost like a parity bit. Make a correction and then continue on and on. And the hope, and we at QuEra are one of the leaders in quantum error correction, but the hope is by doing that correctly, you'll be able to really fulfill the promise of quantum, which is creating and solving these really complex problems that couldn't be done.
Yuval, can you maybe, you said, QuEra is leader in this field. When I interviewed Jan Goets from IQM, he said, on superconducting, at the moment we are between 700 and 1,000 physical qubits, error correction ratio to one logical qubit, but he expected it to be around 2033, around 20 or 30 physical qubits for one logical qubits, and they were moving to, even though they were on superconducting, he expected them to move to new error correction methods. So let's assume that he's wrong and they don't move to 2030, but they move to 50. But where is QuEra today on the error correction ratio, and what is the progress you see on the 5 or 10 year view?
So let's talk about logical qubits and error correction. First, let's go back to giving a classical example just to illustrate this. Let's assume that you and I were talking and I'm outside. I'm not sitting in a room, I'm sitting outside and there's wind, and so sometimes you don't hear me very well. And I want to give you my credit card number. And it's really important that you get it correctly because you're going to make this really important purchase, and if you get one of the digits wrong, then that's not going to work, right? So one way to go about it is, if you can't hear me really well, maybe I repeat every digit several times. So maybe if my card begins with 4 and 5, I say, hey Frank, it's 444, 555, and then I continue to the other digits. So by repeating every digit 3 times, I increase the chance that you'll be able to hear enough times correctly. Now, if it was really windy, or it was even more important that you get the numbers correctly, maybe I repeat each digit 5 times, or maybe I repeat each digit 23 times, right? So the more times I repeat it in this simple case, the lower error rate you're going to get. Maybe you move from 1 in 1,000 to 1 in 1,000,000. So first, when you think about logical qubits, they're not all created the same. What is the error in the underlying physical qubits? Obviously, the better physical qubits, the easier it's going to be to make good logical qubits. Then you ask yourself, how many errors could I overcome? Could I overcome just 1 error? Could I overcome 2 errors? Can I fix them? Can I not fix them? And so there are many different ways.
This also has to do with the steps and the depth of the calculations. Is that correct?
Right. Yeah. So there are many different ways to build logical qubits. Having said that, you can imagine that if I can move qubits around and if I can make parallel operations, then I have methods that are not available to me if my qubits are static. Let me give you a sort of a simple example, using my hands. Let's assume that my hand is a logical qubit, and it's got 5 physical qubits, right? So they kind of move together, and that's how we use to correct. And let's assume that this other hand, so I've got 2 hands, and they're both logical qubits, right? 5 here and 5 there. Now, if I wanted to make an operation between them, I basically want to make an operation between every qubit in each group. So I want to make between this finger and this finger, and so on, every pair of fingers. If I'm a neutral atom qubits, I can take one hand, basically bring it to be almost overlapping with the other hand, and now with a single pulse of light, create that operation, execute that operation between every physical qubit, all at the same time. If I'm a static qubit, I can't do that all simultaneously. I have to do that one by one. When I do that one by one, errors can propagate. Because if there was an error in the second pair, maybe it propagates to the third pair. So by doing parallel operations, I can reduce the number of errors, and by moving them around and having flexibility in the connectivity, we can make more efficient codes. So I'm really glad that
I have an analogy that pops up in my head. I don't know if it's correct, but let's check. I'm quite close to the telecom operators, and you have fixed line operators and you have wireless operators. The benefit of the fixed line operators is they are connected with fiber. So they have very good throughput. Mm-hmm. And the reliability is very hard. But it's quite costly to connect one endpoint to another endpoint because you have to draw a fiber between them. That's maybe the superconducting approach or other. And you're saying, no, look, our atoms are mobile, wireless, and you don't need the cables, and we can bring them very closely, and we make a wireless connection without the cables. Is it a correct?
Yeah, that's analogy? A reasonable analogy. But now let's see what it means. So let's assume that I was a fixed operator, right?
Yes.
And so I have 3 points, three exchanges. So I've got one exchange A connected to B and exchange B connected to C. What happens if exchange B goes down? Oh my God, now A and C are no longer connected, right? Because they used to go through B and now nothing happens. But if my tower is on a truck and I can just drive the truck over, then I'm able to overcome the fact that B is now gone, because now I can create a direct connection between A and C. It gives me that ability to move my towers, my atoms, my qubits around, allows me to have greater flexibility in that.
And what I wonder is, typically the fixed line connectivity, the fiber, is better than the wireless connectivity. Because with wireless, if you have a wireless, let's say you have a 5G or a Wi-Fi signal, then if there's a magnetron in the room or if there's other noise, it's more susceptible to noise. But the fiber is more in a controlled environment. What is the trade-off there between the two? So I think it's a massive benefit. The wireless is a massive benefit, but what is the trade-off? And how can you mitigate the risk of that the wireless connectivity has more risk for...
Well, like many analogies, this analogy also has its limits.
Yes.
Right. And so you can think about, if you go 5 years back in time, we were all, young and handsome, right? People used to say, yeah, we understand that neutral atoms are exciting and they got all this potential, but the operations are not high fidelity. We've got a lot of errors, It's not that you're succeeding 99% of the time, you're succeeding only 95% of the time, and that's not good enough. That was some years ago. But neutral atoms have made this dramatic improvement where the fidelities are at least as good as superconducting qubits. And therefore, some people say that neutral atoms move from being the dark horse of quantum computing to being the workhorse of quantum computing. Because now you can do all these amazing things with them.
And what caused that? What caused the fidelities to significantly improve?
Well, people like Professor Vuletic and Professor Lukin and scientists at QuEra and scientists in other institutions that are not affiliated with QuEra have done amazing work on finding, improving the science, improving the technology, improving the calibration, figuring out where noise is coming from, and doing that. Maybe better lasers, better controls, finer this, so many different things have happened.
And going forward, because, for example, with self-driving cars, they say it's not about reaching the 99, but it is about the 5 nines, 99.99999. It's really about what's behind the 99 point, and then what is the roadmap there? What do you think is realistic on a 5 and 10 year view, and what do you need to get there? What are the biggest bottlenecks?
Yeah. And this is where error correction comes in, because I and of course many other people don't believe that physical qubits can become good enough for these long calculations by themselves. That's because if we had perfect physical qubits, we wouldn't need all this mess and complexity of logical qubits and quantum error correction. The qubits would just be perfect. Life would be much simpler, but they're not. And that gap between where physical qubits are today and the error rates that are required for truly useful calculations are just too big, and that's where error correction and logical qubits come in. Now, I do want to go back to a point you've made earlier. Every technology has its drawbacks. No modality is perfect. So, for instance, one of the things that we have to address in neutral atoms is what's called atom loss. An atom, sometimes would drop out of the tweezer, and we have to be able to detect it, and we have to be able to replenish it. It's almost like these old beer songs, 100 beer bottles on the wall, one of them fell, now there's 99 left. And so if you start with 100 atoms and they fall over time, then at some point you have no atoms to do the calculation. A major result that came from Harvard a few weeks ago was they were able to show that they were able to continuously operate a 3,000 qubit array by replenishing and adding qubits to it. So they basically had sort of a conveyor belt that generated new atoms and brought them into place to allow for this continuous operation. Superconducting.
Wow, that's quite powerful.
It is amazing, and there's some amazing videos on that. But so superconducting don't have these issues, right? The Josephson junctions don't just disappear. And the other thing that if I were representing a superconducting company, I would say, well, but superconducting qubits are really fast. You can make really fast calculations, and all this story that you're telling me about neutral atoms and how they move, these movements take time, and therefore your calculations are slower. And there's a counter argument to that as well. But the point I'm trying to make is no technology is perfect. If there was just one technology that was perfect and nothing else came close, then everyone would stop doing what they're doing in these other technologies. And, I'm sure that all the companies, you mentioned IQM or others, all of these companies that are doing other modalities believe in what they're doing, believe that they can overcome some of the challenges they have, believe that they have enough money to get there and enough patience, and otherwise they're not doing it just for fun. They're doing it because they probably share the same goals, to solve classically intractable problems.
What I found also interesting is maybe the parallel with photonics, quantum computers. And I interviewed QuEra, Stefan Hengersbach, the CEO. And what he mentioned is they have flying qubits, and they could also adjust new qubits into it, and they could reuse them. Is that also the case? Do you have flying qubits for neutral atoms, or is it just totally different? Or what is the difference between using an atom and a photon?
Well, an atom could stay in place, and a photon keeps moving. That's certainly one thing. How do you entangle? Photons bring a completely different layer of complexity. Every technology has its complexities, and one of the things that we find today that customers are sometimes confused. And they're confused because every vendor, every type of modality can put a PowerPoint together that say, we're going to have this amazing computer in 3 years. And so if you're a user, say, okay, so what's the difference between this and that company? Who do I believe? Everyone putting a PowerPoint is simple. And what we are trying to tell the market is, yeah, PowerPoints are good, but talk is cheap, right? Talking about a quantum computer is easy. Building one is more difficult. And so we published a set of 9 steps or 9 achievements that every company should be able to demonstrate if they believe that they have a large-scale fault-tolerant quantum computer. So, for instance, if you have a quantum computer company and you haven't been able to show a single qubit yet, then it's probably not very believable that you'll have a working computer, large-scale error-corrected working computer tomorrow morning. So have you shown a qubit? Have you shown stable qubits that can last for a long time? Do you have a credible way of scaling them? Do you explain are you relying on miracles, or are you relying just on engineering? Have you demonstrated a logical qubit? Are you able to do what's called universal operations? Are you able to make any operation in your quantum computer, or only addition, right? If I were to take a classical analogy. Do you have experience in deploying a system, whether on the cloud or on premises? So all these things that are not specific to one technology or the other, we think that customers should be looking at and objectively trying to see where other vendors are. So talk is cheap, but show me stuff. And if you can't show me, then that's fine. That just means you have more work to do, and therefore the claims that you'll have a fantastic computer in 2 years are probably less believable than someone who has shown maybe 6 or 7 of these 9 steps already working.
I think it's a really interesting framework, and yeah, it makes sense. But sometimes people optimize for the long term versus the short term. And maybe let's dive into that. But before we dive into that, on scaling the amount of qubits, I want to take one last question on the technology. What is the role of magnets? We didn't really talk about it. Magnets and also vacuum chambers.
What's the second thing? I'm sorry?
A vacuum chamber. Are vacuum chambers involved? With,
vacuum chambers. Okay, sorry. I misheard. The process of getting qubits into the computer starts with what's called a magneto-optical trap, MOT. And so you can imagine that a magneto-optical trap has a magnet in it, or magnets in it. So basically it's a combination of both laser light and magnets that are able to start capturing the atoms, moving them in the right direction. They don't just get into the tweezers by themselves. You have to sort of bring them in there. You have to do sort of slow their movement, which is related to cooling. So a magneto-optical trap or magnets are really a core part, other than lasers, they're really a core part of the system. And a vacuum chamber is where the atoms operate. Obviously, if it's not in vacuum, then you have other types of atoms. They can collide, they can interfere, they can block some of the lasers. So you really want to create a situation where you just have the atoms that you care about, in our case, rubidium atoms, and not other types of atoms. That's why a vacuum chamber is very important.
Okay, thank you. Then maybe on scaling the amount of qubits, I think Microsoft had a paper with QCI where they said, okay, at 100 logical qubits, it's the first applications are possible, but you cannot really do meaningful stuff with a quantum computer. With the 2000 logical qubits, then we can have the ChatGPT moment, and also some quantum mechanical problems can be solved. How I look at it, how I try to analyze it, I think there are three ways to get to 100 and 2000 logical qubits. I think the first way is just like AI, scale up, more qubits per chip. Not sure how that works for a neutral atom, because there's not manufactured, they're neutral. Then the building scale out, so building clusters of qubit chips. So then you need to have the network connection between them. And C, the error correction ratio. And for me, the developments in both forming qubit clusters and the error correction ratio, the improvements of that on a 5 or 10 year view are underestimated by the market. But can you walk me through how does this work for neutral atoms? So can you walk me up for, okay, what are the big data points that help you to scale up the amount of qubits per chip or qubits per machine, or how does that work?
Sure. So first, I think we agree that the more qubits you have, or the better qubits you have, better logical qubits, open up new applications. I mean, if we go back classically, if I give you a car that can drive only 200 kilometers before it runs out of energy, it's still useful. It's not useful for everything. You can't go from Amsterdam to Milan, perhaps, with such a car and come back. But you can certainly go to the grocery store. You can take your kids to a ballet class or something like that. And if you had a car that had 1,000-kilometer range, then that's great. That's better. So if you have 100 logical qubits that are good, you can solve certain problems. If you have 500 logical qubits, maybe you could solve a bigger set of problems. For us, scaling is about a couple of things. First, we did discuss laser power. So if a tweezer requires a certain amount of power and you want more tweezers, then you need to be able to put more power in the system. The other thing is about...
Can you quantify that, Yuval? So what is the power your most... Is it like ASML, they worked with Cymer, and they had a maximum laser power, and then they upgraded over time. How does it work for... Is it one laser that requires more power, or do you need multiple lasers, or how does it work? I'm not familiar yet with that.
Well, I believe that today we have one laser, but if you go to we always say, okay, we go to the laser manufacturers, and can you do a little bit more? Can you make it more stable? Can you make it more reliable? I mean, I go back to the car. If you drive your car, if your car was designed to drive at 80 kilometers per hour, and you drive it all the time at 200 kilometers per hour, ignoring what the police would think about you, and maybe the car was not designed to go all the time at 200 kilometers an hour, or if the car was designed to go forward and you drive it all the time in reverse, maybe something will happen, right? So we do sort of push the laser manufacturers to do better, and at some point we may need multiple lasers because, or it may make sense to put multiple lasers. The other thing that we need is, we spoke about the microscope that takes a picture. If we have more and more qubits, then we need a microscope that has a wider field of view, bigger field of view, wider lens, or do something else. If you want to run really long calculations, we spoke about being able to replenish atoms for continuous operation. If you want to do error correction, you need to be able to quickly measure atoms and decide and do something that's in sort of inside the industry, this is called mid-circuit measurement, being able to do a measurement in the middle of a circuit and feed forward, meaning do something based on that measurement. It's sort of the equivalent of an if-then-else statement in classical computing. So we're not there yet. I mean, we still have problems to solve. It's one of the things that makes this industry exciting. But it goes back to an earlier comment that I was making, that quantum computers are not very useful today, except for some scientific discovery and for preparing for the time that they will be, because you do need to learn how to program them. You do need to learn how to connect classical and quantum computers. There's a different way of thinking about quantum programming, just like there's a different way of thinking about GPU programming. So it doesn't happen overnight, right? I sometimes give the example, you're not a medical doctor, I believe.
No.
And if you had to take a medical exam and it was critically important to you, and you had to take it tomorrow morning, likely you would fail. Even if you studied all night, you would likely fail. But if you had to take it in 2 years and it was critically important to you, then maybe you could create a plan on how in 2 years you will get good enough so you can pass the exam. Same thing in quantum. If you believe that quantum computers will be powerful and useful in 2 or 3 years, you have to start now. You have to start studying and learning and choosing the vendor and learning how to do it now. Otherwise, you're going to be in that overnight situation where someone else knows how to do amazing things with quantum computers and you're just a novice there.
And Yuval, you mentioned that's a little bit about increasing the qubits per system. And maybe system is a better word than chip. But then how does it work of forming clusters? So if you have one system, you mentioned, okay, maybe we can have multiple lasers. But let's say you have one laser and one system. Can you then connect and entangle multiple systems together?
Yes.
So to scale out. And how does that work for neutral atoms?
Well,
and then do you need to would you use photonics to do that, or can you keep them in neutral atoms, or how can you do the connection? How would that work?
So I think for every modality, scale out is a possibility. For some modalities, it's more urgent because they can only do small chips or a small number of qubits in the machine. I think most people think about optical networking as sort of the way to optical links is the way to entangle adjacent machines, and of course that means that you have to potentially make a conversion between whatever modality that you're using, superconducting or something else, to photonics. How fast is that link? What are the errors? How does that impact connectivity? If I have a 10,000 qubits where every qubit is connected to every other qubit, but now I have a link between groups of 10,000 qubits, that introduces software issues as well. I think that's one of the perceived advantages of photonic quantum computers, that they say, well, everything is photons anyway, so we're not worried that much about connecting. I mean, we are connecting all the time. So yes, we are thinking about how to interconnect machines and what that means. The good news is that for us, it's less urgent than some of the other modalities.
Mm-hmm. But I think to your point, on the medical exam, if you have to study and prepare for it, I think that really scales. So now with AI, and AI is absolutely different than quantum computing, because you have no entanglement and no superpositioning. But now they're going from 10,000 GPU clusters in 2023 to 100,000 in 2024, to 1 million in 2027, and potentially 3 million in 2030. So that was massive. That if you're able to do scale up, that would bring massive benefits.
Yep, it brings lots of benefits, and it brings lots of complexity. So I agree with you. It will need to happen. We are working through some of what we think is the best way to do so. And ultimately, yes, computers will be networked, whether just to scale out, or sometimes you can almost think It's not exactly like the internet, but you could say, can I distribute a calculation between computers that are far away? If you have a big quantum computer and I have a big quantum computer, can we somehow network them together to solve an even bigger problem? But that's sometime into the future.
Yes, and maybe to summarize to your point, this is not where the focus is on right now for neutral atoms, because you have a natural way of scaling the amount of qubits per system.
Right, that's not the most urgent thing, yeah.
Yes, and that is where the focus and the priority is at the moment. So you're not reliant on. And then the third element, the error correction ratio, and that's where you were also quite bullish on. Could you walk us through the improvement? So where are you today on physical to logical qubits, the error correction ratio, and how do you expect that to develop for the coming 5 and 10 years?
There's no right answer on how good you need to be, because it depends on the problem, right? So we have shown
more on
experiments
the progress that you expect to make.
Yeah.
So where are you in 2025? What do you expect in 2030 and 2035? And of course you will be wrong, but what is your best guesstimate?
We have shown, so error correction codes are measured in many different ways, but usually they're measured in 3 numbers. The first number tells you how many physical qubits that you're using to generate the logical qubit. The second number tells you how many logical qubits you're making out of these physical qubits. And the third number tells you something about how many errors you could detect and correct. And so for instance, some of the work that we did is using what's called the 713 code. The 713 code means that you're using 7 physical qubits to make 1 logical qubit. And the 3, I don't know why, I mean, I know, but it doesn't matter for the purpose of this discussion. 3 indicates that using this code, we can detect and correct 1 error. If, for instance, it was only 2, that means we could detect an error but not correct it. And we know that an error was there; it's still useful. And so, when you move to higher and higher codes, usually the first number increases. So maybe it's not 7, maybe it's 17, maybe it's 49, right? And you also want to increase the last number so that a code can be more and more resilient. If you had 2 simultaneous errors, if you had 3 simultaneous errors, then you could still detect and correct them. I think the code itself, I mean, so we have lots of flexibility in the codes, and actually in our systems we're demonstrating different codes, which is also some of the power of the flexible connectivity between the atoms. What ultimately matters is the number of logical qubits and the logical error rate, meaning is it 1 in a million? Is it 10 to the minus 8? Is it 10 to the minus 10? And so on. And so we're getting better and better. You know, we're moving towards hundreds and in the future thousands of logical qubits. We're moving towards error rates that are truly meaningful. I'm not going to reveal our entire roadmap on this podcast right now. That's probably coming in a couple of weeks. But yeah, that's obviously an area that we are heavily invested in looking at new error correction codes and looking at ways to decode them. One of the things I mentioned that NVIDIA is one of our investors, and we're also doing some technical work with them. So we published work that used an AI decoder, meaning an AI model, to help take data from a quantum computer and understand where the errors were and how to correct them. And that shows promise over sort of conventional decoders. You know, as these logical qubits become bigger, the classical computational complexity of detecting and correcting errors become bigger, and therefore this is an area that AI might come in useful, where AI could help quantum.
Okay, clear. Thank you for explaining that. And at the moment, can you quantify where you are today, or what's the last number on logical qubits and the error correction ratio from physical to logic that you published?
I have to look up. So much published work between us and our collaborators in Harvard and MIT that I don't want to give you the wrong number.
Okay, now let's leave that out. And maybe for the audience, I really liked the 3-minute video on QuEra. I thought it was excellent, describing the basics of neutral atoms. was very
Thank you.
very clear. What do you think is the tipping point in your roadmap? And what do you see as the biggest technical bottlenecks?
There's an interesting trade-off between, quantum computers are difficult, and installing them and servicing them is difficult. And we are primarily focused on the future, meaning that the devil is in the details, but if you gave me a purchase order to build and install 50 quantum computers today for delivery next year, then maybe we could do it, but maybe we're not interested because we don't believe these quantum computers are sufficiently powerful, sufficiently useful, that are worth distracting our efforts from building next generation quantum. Building next generation quantum computers requires capital, which we now have, requires that we continue to expand the team, both in science, in engineering, software engineering, for instance, expand the team that works with customers to implement algorithms on our computers. One of the things that's, because this is an early stage industry, then it's unrealistic to assume that the same algorithm would perform equally well on all types of computers. And so we believe in what's called co-design, where we work with customers to select problems that can take advantage of the capabilities of neutral atom computers and then optimize the hardware, the error correction, the software, everything from top to bottom to try to squeeze as many results and as much performance as we can from the current generation of computers. At some point, that will not be necessary, right? If I give you a computer with only a classical computer with 64 kilobytes of program memory, you'd have to make gymnastics to fit the program that you want in there. And if I give you a computer that has gigabytes of program memory, then life is easy. You could be much more wasteful. You don't have to be as efficient. Maybe you don't have to code in assembly language anymore. You could use a high-level language and it's going to be fine. So we are in an early stage of quantum computing, and therefore, the hardware needs to grow, the software environment needs to be better. People who run high-performance computing centers need to get more and more experience in, what does it mean to install a quantum computer? What does it mean to service one? How does one connect it to classical applications? So a lot of things to do. We're far from done.
Okay. And how do you see the neutral atom architecture integrate with classical computers or with other quantum technologies?
Our focus is really integrating with classical. Obviously, some things, I don't expect that we'll ever have a Zoom call on a quantum computer, right? Some classical computers are better in some things, and quantum computers are expected to be better in others. So one has to both create the workflow. So maybe a classical computer does pre-processing. Maybe there's classical computing that's part of the error correction. Maybe classical computer does visualization and post-processing, or database queries, or internet or fetching from a database. So a quantum computer is less likely to work completely in isolation. And so we're investing a lot of time in working with classical vendors to figure out the workflows, the scheduling, the assignment of jobs. How does one know that one ends? All the things that high-performance computing centers know, how to service multiple customers, how to give priorities, how to do this, how to do that, how to do billing. So things that maybe are not related specifically to quantum mechanics, but are more related to putting quantum to work, to putting quantum into the real world.
And on that, of putting it in the real world, I think we also need innovation in quantum algorithms. And how do you see software and compiler stacks for neutral atom computing? Do you think that algorithms need to be rethought to exploit your architecture?
I go back to the CPU versus GPU example. If you take a program that runs on a CPU, you could theoretically run it on a GPU, but you don't take advantage of the parallelism that a GPU could give you. So people had to rethink, I can do FFT in a different way. I can do matrix multiplication in a different way, right? Same with quantum computer. You could write simplistic programs that don't take advantage of the power of the quantum computer, but then why bother? So if you think about neutral atoms, there's certainly work that we are doing with compiler vendors to say, okay, what would it take for you to write the program in a way that would be parallel, that could take advantage of this flexible connectivity? And then there's a lot of low-level stuff. Which qubits do you move to where? Do you keep qubits in the processing or entanglement zone, or do you move them back to memory? Which quantum error correction code do you use? Does it make sense to switch codes in the middle of the calculation because some codes are better than this and others? So there's tremendous amount of work to be done at the software stack. We have a lot of software partners. We put together a partner program called the QuEra Quantum Alliance, where we basically said, look, we think we're the best in the world in quantum computers and certainly in neutral atom quantum computers, but we're not best in the world in quantum chemistry, and we're not best in the world in compilers. So let's bring partners together that believe in the story, and let's go and serve customers together, delivering what customers want through a combination of best-in-class vendors from each field.
Okay. And Yuval, maybe on the technology, how does QuEra decide what to do in-house and what to do to outsource? So in the past, IBM and Google, they did everything, and IQM, they did everything in-house. But now they say, okay, now you see the start of some specialization in the sector. And how does that work for QuEra? What are things that QuEra would say, okay, here it makes sense to outsource and not to do in-house?
Yeah, I don't know if it's different for QuEra than other companies, but basically you have multiple considerations. You say, how much better is the external vendor than what we are today and where we could be with reasonable effort? How strategic is mastering that technology? Is it okay that we have someone else do it for us, or is that something that's truly an area of research that has a lot of potential IP that we have to have internally? How dependent might we be on that supplier, and is there a risk that that supplier gets acquired or goes out of business? And if they do that, what would happen to us, right? So if this was just sheet metal production, right, there are many companies who can make sheet metal. It's not strategic to us. We can have it here, we can have it there, and if someone goes bankrupt, that's really unfortunate, but we'll find someone else. But other technologies may be more strategic. So do they require any special talent? Do we have the talent? Could we acquire that talent? So, I mean, sort of the usual considerations, I think, for any company.
Is it fair to say that there's now an acceleration of specialization and outsourcing? And do you also see that at QuEra? Or okay, can you quantify that a little bit and put some context around it?
I personally haven't seen a dramatic change in that. Obviously, when a company is truly small and just starting, it's a little bit more difficult to find people that want to work with you. But then you have maybe a greater set of needs. Over time, there are things that we know how to do well internally. Maybe things that we developed internally because there was not an outsourcing option at that time. Now there is. So, okay, well, are we good with what we have, or do we need to sort of cross the river and do something else? So I haven't personally seen a dramatic shift in the desire of companies to outsource relative to a year or two ago.
Thank you, that's helpful. Can you walk me through your main suppliers?
Well, it's a complex system, right? We need lasers, we need optics, we need cameras, we need high-speed control electronics. So some of the specifics of the suppliers, who do we use, that ends up being a little bit on the proprietary side. But yes, we don't build our own lasers, we don't build our own cameras. So we work with suppliers that do, and work with them sometimes very closely to get the special requirements that we have. In laser power, we spoke about wavelengths or stability or power or reliability, and so on and so on.
Okay, interesting. And then the other thing is, are there areas where you think that because, for example, of AI, a lot of talent and capital moves into, and it brings much more scale? One example is now CPO, co-packaged optics, that for photonics, that was, the idea was spoken and thought many years for, but now with NVIDIA and Broadcom moving to CPO, then that brings much more scale. Other things, maybe material choices like rubidium or molybdenum, that you can benefit from significant scale, and that really gives you some advantages given the fact that you are already positioned there.
Yeah, I mean, I think that when you increase the number of qubits and you start thinking about, okay, we have more laser beams that we need to say switch and so on, then one of the things that comes into play is photonics integrated circuits. So circuits that allow us, that combine, silicon and light, that allow us to switch and route light in more efficient ways. That's definitely one area that we've published a little bit and we're working on.
Maybe what is extraordinary of QuEra? If you have to summarize it in 1 minute.
The people, the caliber of people, the talent pool, the desire to solve truly difficult problems is really extraordinary. And I think part of that does have to do with our close proximity and close relationship with Harvard and MIT. Something that has to do with sort of the caliber of the scientific founders. Professor Lukin, Professor Vuletic, Professor Greiner, Professor England. So I think the people are extraordinary. Present company excluded, as they say. But,
I find it really interesting.
All the other people are extraordinary, right?
But I think in life quite often it's about people. It's people business and people make a difference. That's interesting that you mentioned it. I want a little bit talk about the barriers to entry. How hard is it to copy QuEra?
Yeah, I remember that on one of the episodes of my podcast, I interviewed the CEO that runs a silicon qubits company. And every CEO that comes on the podcast says, "Oh, my technology is great, and it's much better than this, it's much better than that." And so sometimes a good question is, well, if it's so good, then why is not everyone doing it, right? And he said, well, because it took me 20 years to get the level of expertise in this particular field. And if you started today, maybe you're really smart. It'll take you 10 years to learn what I learned in 20, but it's going to still take you 10 years. I sometimes say, if you are a professional oboe player, that doesn't mean you can play the violin tomorrow morning, even though you understand how to read music, right? It takes practice in your particular field of expertise. So it's really difficult. I mean, there is both IP that's protected, but there's certainly so much know-how. Yeah, when you say, oh yeah, I just shoot lasers at atoms and I bring them nearby, that's very easy to talk about. We spoke about that earlier a little bit. Talk is cheap. Building a quantum computer is much more difficult.
Okay. Yuval, we didn't talk about business momentum, but I also want to talk a little bit about business momentum. So can you walk us through customer adoption? And you mentioned already, okay, the computers is not so far, they cannot solve a lot of problems, but what is the business momentum and do you have concrete data points that prove that there's demand for the solutions?
We engage with customers in 3 ways. One is we allow them to use our computers over the cloud. Our first computer, it's a 256 qubit machine, is available on the cloud through Amazon since November of 22. So we're very close to celebrating its 3rd birthday. And it's been used by hundreds of organizations around the world, JP Morgan, BMW, many others. It's been used to create some groundbreaking scientific research. And so we definitely see use. And when we started with Aquila, that computer, we only had it available for 10 hours a week. Now we have available for 130 hours a week, almost the entire week. Part of that was we got better at running it, but part of that was demand. I mean, we just didn't want to have customers wait 2 weeks to get time on the computer. So we've got real proof that customers do very interesting stuff with it. The second way we engage with customers is by selling them a machine for on-premise delivery because they want it in their data center or in their country. And so, for instance, last year we announced a really important deal with AIST, the Japanese Institute of Standard and Technology. We sold them a computer. We installed it recently for over $40 million. So that's proof. Someone is willing to pay you $40 million, then surely they think you have something that's truly valuable and interesting. And the third way we engage with customers is by doing co-design. That work of optimizing hardware to software and vice versa. And so, for instance, we recently published work that we did with Los Alamos National Labs in the US. We published work that we did with American Amgen and Deloitte. So we're doing algorithm development projects with customers. So cloud, on-premise, or co-design. We are seeing momentum and we're seeing success in each and every one of these fields.
That's clear, thank you. How do you see the total addressable market for neutral atoms?
The total addressable market for quantum computing is tiny today relative to what it's going to be in 5 years, because quantum computers are not as useful as they will be.
Let's say 10 years, I think, because, yeah.
We're not worried about total addressable market, because quantum computing can impact essentially every single market vertical. When you think about key applications for quantum computing, people think about simulation, they think about optimization and machine learning. And give me an industry and I'll tell you simulation problems that they have, optimization problems that they have, and machine learning. So these are horizontal applications that can impact and transform practically any industry. And so we're leaving the estimations to companies like BCG that are, by the way, one of the QuEra Quantum Alliance partners that estimate billions and billions of dollars in addressable market. Probably they're pessimistic. I mean, I think it's going to be much more. We're not worried about the market. We're worried about how quickly can we build large enough error-corrected computers that people can use.
Okay, that's clear. And when would your conviction go up, Yuval, that neutral atoms are scaling? What do you need to see? Which 2 or 3 data points and say, well, Frank, if that happens the coming 3 or 5 years, then my conviction goes up that we made it.
What I've seen, I've been 3 years at QuEra, give or take, a little bit over 3 years. And in these 3 years, because of the hard work that our scientists and engineers have done, challenges have transitioned from being primarily scientific challenges, oh, we don't know if we can do that, to primarily engineering challenges. Yeah, we can do that, but now let's make it reliable and scalable and manufacturable and so on. So in that sense, although it's not truly a straight line, my conviction goes up every day because we're knocking out the scientific problems. They still remain, every time we get to a peak of a mountain, we say, okay, what's the next mountain that we can reach, right? Yeah, 3 years ago, putting a system with 256 qubits online was just an amazing achievement. And 3 years later, Harvard is publishing, 3,000 qubits that operate continuously. And it's just, the rate of progress is stunning. And that's one of the reasons that I so much enjoy being in this market.
I can imagine. Okay, then can you walk us through the positive flywheel? So why can QuEra innovate the fastest, and why are you the best longer term?
Well, let me start from the second part of your question. We believe that neutral atoms is the best modality. And that's because of room temperature operation, perfect qubits, all-to-all connectivity, scalability, all the things that we discussed previously in the podcast. And so we believe that neutral atoms is the best way to get to quantum computer. And we believe that quantum is both the scientific and commercial leader in neutral atoms, because we have shown that we can deliver systems, that we can put systems online, that we can run error correction like no one else. So we are convinced that we are today the leader in neutral atoms, which happens to be the best modality. That doesn't mean we have to continue running, right? We have to continue innovating and hiring great people, making sure we have enough money, and so on. So that's all there. But the flywheel comes from creating better systems and at the same time listening to what customers want. listening to what customers want, working with customers. Oh, we tried to do this. It didn't work. Why did it not work? Okay, we did this with 200 qubits. Is that good enough for you? Okay, what? No, it's not good enough. Why is it not good enough? What do you really need? And that listening to customers and then being able to quickly transition it into adjusting our work plan accordingly, that the proximity to Harvard and MIT and the quality of people that we have and the quality and amount of backers that we have make us very optimistic about the success of QuEra.
I've got two more questions. One is, how much capital do you need?
Well, building quantum computers is expensive. We're fortunate to have done a very nice raise, $230 million, led by Google and SoftBank, and of course, with our existing investors. NVIDIA also joined. We need enough money to operate. By the way, there's a risk to having too much money. If you have too much money, then maybe you're not taking care of it the right way, so to speak. Maybe you're having the right amount of money, and I think we are at that sweet spot. Remember that commercial companies also need to be able to return money to investors and return a profit. So if you raise $2 billion and your investors, you raise $2 billion and and let's say you gave up 20% of the company for that, then that means the company has to sell or IPO for much, much more for the investors to make a good profit. So we're not here just for the science, we're also here for the business. One thing that, although is implicit in what we spoke about neutral atoms, is when you go to vendors, you should ask them, okay, let's assume you need 1 million qubits to make something truly useful. How large is it going to be physically? How much is it going to cost? And how much energy does it consume? And some of the approaches that we're seeing are saying, oh yeah, we need a football field, it's going to cost $1 billion, and it's going to require 100 megawatts of power. That reminds me of a B-2 bomber. A B-2 bomber, a very unique plane that costs $2 billion, and of which 20 or 20 something were made. We think that because we don't need cryogenic cooling, we operate at room temperature, because we can put lots of qubits on a single machine, then our machines will be much smaller physically, they will be much more affordable, and therefore a much larger group of people can afford them, and they will require tens of kilowatts of powers and not tens of megawatts. So if I were just to continue the airline analogy, I think we're building the 777, the Boeing 777, or if you want the Airbus A3, right, or of quantum, not the B2. We think that this is the right technology to make something that's truly useful and widely available to anyone, any friendly organization that can use it.